we can integrate functions of the form of this, and then some rational function like this, if the degree of q is bigger or equal to the degree of p plus 1. And instead of cosine, we can have sine. We do this by considering the integral of e to the iz of p of z of q of z over some contour which depends on y and r, like this, and the contour is chosen like this, where this is minus r and this is r, and we're going up by height of y, like this. So this is r plus iy. Okay, and we have to do this in the smart way. If we take the limit, first the limit as y goes to infinity of this thing, and then the limit as r goes to infinity, then this thing, e to the iz, of z over q of z, does turn into just the real part, which is the integral from minus infinity to infinity, e to the ix p of x over q of x dx. And then we read off the cosine from this as the real part of this integral, and read off the sine as the imaginary part. Yeah. Okay. Important thing to remember is not to try and rewrite this as the complex trig, and then work with that. Instead, just write this as e to the iz. That's the form in which it will work. Okay. So when we did these integrals around 0 to 2 pi, we rewrote the sine and the cosine as their complex. We rewrote them using our knowledge of the complex version of them. We don't do that here, so don't mix that up here. All right, so that's just a recap. Let's actually do it on some specific example. And our example is this one: integral from 0 to infinity of x sine of x over x squared plus 9 dx. So we will consider integral over this kind of a contour, gamma y of z e to the iz over z squared plus 9 dz. So I'm not going to go over again the fact that these parts will vanish as we let these limits go to infinity, first y and then r. So we're just going to take that as given, and we're going to calculate this guy. And if we choose r and y large enough so that we contain all of the poles inside this expression, then that thing will give us our answer. And that's all we need to do. Yeah, that's all we need to do. Because this thing, as you can see, has just got finitely many poles, in fact just 2 in this case. So for large enough r and for large enough y, we have that this thing will contain all the poles it possibly need to contain in the upper half plane, the only one of them. Yeah. And it's only true that in the limit as y and r goes to infinity that this thing is equal to this, but as soon as we have r and y big enough to contain our one pole, then the contour is going to be exactly the same no matter how big r and y is. Yeah? Cool. So we just need to focus on calculating this for sufficiently big r and y such will contain the one pole. What is the one pole? Well, we have z squared plus 9 can be factored as z minus 3i, z plus 3i, right? So therefore, our one pole is here at 3i. Oops, this is 3i. This is where the one pole is. Yeah. So assume r and y is big enough so that it contains 3i, and then let's figure this thing out. So the one pole we have is a simple pole. It's a simple pole. Yeah. So let's simplify notation a little bit. Let's write f of z is this weird function z e to the I z over z squared plus 9. So we want to calculate the residue at 3i of this thing. F of z like this. Since it's a simple pole, the formula for this is not too difficult. And this is the limit as z goes to 3i of z minus 3i f of z. Let's write out what this is. This is the limit as z goes to 3i. And what do we have? We have z e to the I z over this thing. Okay, so we're going to do this in one step. So when we multiply z minus 3i to this expression, since this thing breaks up into z minus 3i and z plus 3i, when we multiply this guy through, all we're going to have on the bottom is z plus 3i. Yeah? So on the bottom just we have z plus 3i. Are you happy with that? Yeah? Cool. All right, and then this is perfectly good because this top and the bottom are continuous, holomorphic at 3i, there's no problem, so we can just stick in the values directly into this. So we're going to have 3i, e, and z is now 3i, so it's going to be minus 3 like this. Just minus 3 like this. And on the bottom, we're going to have 3i plus 3i, which is going to be 6i, so it's over 6i. So then this just turns out to be e to the minus 3 over 2, just like this. Yeah? Cool. So our residue is this real number. So therefore, this integral here, let's call this guy star. Make that bigger. So star is equal to 2 pi I times this residue at 3i f of z, and we've calculated it, so this is just equal to pi I e to the minus 3 over 2. Is that right? No, it's not right, because the 2's cancel. It's just equal to this. Yeah? Cool. All right, so if we look back at this expression here, yeah? So we said, okay, let's consider this part, and then the imaginary part of this part will be this thing over here, yeah? And our answer is that this guy is just imaginary. This guy is just imaginary. Do we believe that? Do we believe that? So this thing, if we wrote it out as the real and imaginary parts, sorry, not this thing. This thing, if we wrote it out as the real and imaginary parts, then what do we have? We have the integral from minus infinity to infinity, this cosine of x, p of x. Oh, but let's put the actual polynomial we have, which is this thing. I'm mixing things up. Right, sorry, let's do that again. Let's write this thing here, but let's write it as the integral from minus infinity to infinity on the real line, which is what happens when we take the limit as r and y goes to infinity. Yeah? So this thing in the limit goes to this thing. Yeah? It goes to this thing. The integral from minus infinity to infinity of x cosine of x plus I sine of x over x squared plus 9 dx, right? So this thing goes to this thing. So I definitely don't want you to think it's equal because we have to take the limit. So this thing goes to this thing in the limit, yeah? And then this thing is two integrals. It's this integral from minus infinity to infinity of x cosine of x over x squared plus 9 plus I, the integral from minus infinity to infinity, x sine of x over x squared plus 9. Yeah? This guy on the right is what we're looking for. But the fact that we have that the answer for all large enough r and y is just an imaginary thing, what does that tell us? What does it tell us from here? It has to be 0, right? Because this number is equal to this number if our theory is correct, right? If we did the calculation correct and the theorem is true, then this number is equal to this number. And this is just a complex number. Sorry, this is just an imaginary number. Yeah, there's no real part here. And this has a real and imaginary part. And the only way these numbers are the same is if this real part is 0. Okay. Do we believe the real part of this is 0? Yeah, it's what we call an even function, right? Cosine's an even function. So cosine is even, which means cosine of minus x is the same as cosine of x, right? Even, yeah? And everything else here, well, not everything else, but this entire thing, which isn't cosine, this x over x squared plus 9, this is an odd function, yeah? So a function is odd. So if f of minus x equals minus f of x, then it's odd. Yeah? Yeah? Remember this? Cool. So if we integrate an odd function from minus infinity to infinity, it's going to be 0. Yeah? Because the stuff on the right-hand side, whatever we have there, we have the negative on the left-hand side. Yeah? Yeah? Or at least if we integrate it in the sense of Cauchy principal value, as we integrate from minus r to r and take the limit. Yeah? Yeah? So, I mean, when I asked you what the difference was between Cauchy principal value and the other notion which you teach in calculus, you gave this example, and the reason it works is because this is an odd function. This is an odd function. Yeah? A simpler example would be this, also an odd function, where the Cauchy principal value, the limit as r goes to infinity, as we integrate from minus r to r, this is equal to 0, and therefore it exists, but if we integrate from 0 to r, it makes no sense. Okay, good. So this guy here is an odd function because cosine is even, x squared plus 9 is even, and this x itself is odd. So the product of an odd and an even function is an odd function. Yeah? So we teach this in calculus, or definitely teach it in calculus, and we sometimes give students examples like this, where there's nothing you can do in terms of applying the calculus techniques to show that this thing is equal to calculate this thing. Yeah? But you can just observe that it's odd. You can just observe that it's odd, and therefore it vanishes. Yeah? We'll probably give something like x to the 4 so that they at least know that this integral converges. All right, cool. So far we're happy because this is consistent with what we see when we expand out the integral we're trying to calculate. Yeah. And a corollary, not corollary, but as a consequence of this calculation as well, is that we have that pi I e to the minus 3 should be equal to the sine part, equals minus infinity to infinity x sine of x over x to the squared plus 9 dx like this. Yeah? And therefore, just getting rid of the I, we should have that this is equal to this. Yeah? Which isn't quite what we're looking for because the original problem was this guy. The original problem was this guy. Right? Yeah? And this is not quite the same because, yeah, obviously this is from 0 to infinity, but this guy, this entire function is an even function because x is odd, sine is odd, so producting two odd functions is even. So the integral from 0 to r is exactly half the integral from minus r to r. Yeah? So if we divide this thing by 2, we're going to get what we want, right? So we should have 0 from infinity x sine of x squared plus 9 dx is equal to pi over 2 e to the 3. And that should be our answer. Everybody happy? And notice, as I'm going to keep telling you, just because it's so important, none of our stuff, none of our calculus methods are helpful for this. We cannot calculate this otherwise. Yeah? We cannot calculate this otherwise. Nothing I can think of in calculus would allow you to calculate this. This is completely new territory here. We're doing stuff we could not do before. All right, cool.